Well, let's start out with this example here. Some of you guys have already seen how I work these examples. You know how these go. This example problem, this is going to be, I think I'm going to attach this to lecture 15. I'm going to write down the givens in here, and then I'll go full screen with this so you can see it better. We have a residential heat pump here. That is, and this is a W dot. It's a power input and an M dot. That's a mass flow rate. So we have a heat pump using R134A as its working fluid or its refrigerant. So I've got R134A. They've given me the power input to this device is about 1.2 kilowatts. And this is a heat pump. Hi, Lucy. Do you want to say hi? Yeah. This is Lucy. Say hi, Lucy. Are you good? Can we continue with our video? You're just going to sit on the paper. Okay. I'm going to attempt to ride around Lucy here. She's going to help, as you can see. Lucy, honey, come on. I've got a mass flow rate of 0.018 kilograms per second. I've got some properties here. We need to figure out what to do with those in just a second. Lucy, we don't need any help. They want us to determine or to find, what are we looking for? They want us to find the coefficient of performance for this heat pump. Remember we said previously, COP stands for coefficient of performance. They're like an efficient, it's kind of like an efficiency, but it's not a true efficiency because a COP can exceed 1 or 100%, so it's not a true efficiency. They also want us to find the rate at which this device is absorbing heat from the outside. So everything's given to us on a per unit time basis, and that's fine. We can work these problems either per unit mass, total amount, or per unit time. Thermodynamics is kind of one of the first places where we see that that occur, where we sometimes will work with these quantities on different bases, either per unit time, per unit mass, or total amounts. Now, um, here's where I would say, okay, where should we start? Just looking at this problem, how should we go about trying to find this? And one might say, well, Steve, we've got some equations for this coefficient of performance, right? We're looking at the coefficient of performance for this heat pump. Sure, yeah, we do. And these are similar to efficiency. It's going to be what you want. For a heat pump, you actually want QH divided by what you have to do to get it, and that's going to be the work input going into the compressor. Now, these are per unit time, so I'm just going to put dots above both of these, and that tells me as long as I have heat energy per unit time and energy per unit time, both top and bottom, and make sure the units are the same. COP is a unitless quantity, so I need the same units top and bottom. So I can, again, compute both of them per unit time, and that's just fine. And if we look at, well, okay, let's say, okay, well, what do we know here? Well, I know the power input, and I'm looking for COP. So I don't know QL. Okay. So what else do we have? And again, we get into this problem-solving loop of, well, do I have as many equations as I have unknowns? I'm looking for this. So I've said, okay, here's an equation that helps me maybe get to that. What's known, what's not known? Well, I know this. I don't know that. Okay, now this becomes my unknown that I'm looking for because I got one equation, two unknowns. Now I'm looking for this guy. So what tools, laws, solutions equations could I maybe use to find this Q sub H then? So that gets me to COP. And then a lot of times I'll kind of rephrase the question and say, okay, well, what's a good tool for finding something like an unknown heat transfer? And somebody will say first law. Okay. Um, what's our system? Right? To write a first law equation, I need to draw my system. And when I draw my system, then I can add the ins, subtract the outs, and that allows me to figure out the unknowns. And maybe somebody say, well, it's the heat pump, isn't it? Right? Isn't the heat pump the system? And yeah, sure, okay, we can do that. I've got power in, I've got Q dot H going out, and I've got Q dot L going in. And the first law for that says, well, if I add the in, subtract the out, set equal to change, um, I've got power in. We've derived this already, plus Q dot L minus Q dot H. It's going to be 0 because it's a cyclic system. Okay, I've got now 2 equations with 3 unknowns, right? So what other tools could I maybe use to try to find this Q dot H? The clever student might have noticed, and if you haven't, that's okay. It's kind of new. Um, notice I've got properties at the inlets and the outlets of this condenser where Q dot H occurs. And for students in class with me, I'll look at them and I'll ask, by the way, what is a system? And I'll force us to try to remember that from like day one, right? What is the system? And remember, day one, a system is anything that we want to isolate from its surroundings. Essentially, anything you can draw a dotted line around. So notice that if I say, well, you know what? Let's analyze that condenser as its own system. If I analyze the condenser as its own system, what crosses the boundary for the condenser? Well, I've got mass. It's a heat exchanger, but I'm only looking at one stream in this heat exchanger. I've got refrigerant coming in and out, and I've got Q dot H also going out. And I know properties, if I call this the inlet 1 and this outlet 2, I know properties at state 1 and properties at state 2. You can go back up here and label those now if you like. You can say, well, P1 is equal to P2. It's constant pressure. That's a common thing we'll do for one of these condenser or evaporator units. We'll say that at the inlet, you've got a temperature of 35 degrees C, and then at the outlet, I'm out of room here. We'll say that it is saturated liquid. The problem statement would probably say something like there's saturated liquid exiting the condenser. A shorthand way of writing that is x2 is equal to 0. X tells us it's saturated something. 2 meaning, or I'm sorry, 0 meaning that it's 0% in the vapor phase. It's 100% liquid. Again, the problem statement would say saturated liquid exits the condenser. So I know now properties at the inlet and the outlet. So I've got minus Q dot H, according to the first law for this control volume. This is now a chapter 5 problem. This guy is Q dot H, and rather than say equal to, let's plus the mass coming in. That's M dot times H1, and the mass going out minus H2. I'm not going to worry about the kinetic energy. We talked about how do we know when I worry about the kinetic energies. It's not asking for the kinetic energies. It's not given. I don't know the areas, so we're going to assume that the kinetic energies are negligible compared to the enthalpies. All right, so I'm going to stop share for the moment here and let's look at this full screen and go back over what we've done here. Right, I've got a heat pump with a power input given, a mass flow rate given. We know it's R134 flowing through the system. I know at a state 1 and 2, which we have to make sure we know what is the state 1 and 2. Well, the state 1 and 2 are the entrance and outlet of the condenser. At the entrance of the condenser, I've got a pressure and a temperature, P1, T1. At the exit, I've got P2 and X2. That's enough information to find the heat transfer for this very specific unit, the condenser. I can perform a first law analysis for that. And then I can backtrack my way back up here. Once I've got Q dot H, that allows me to get COP, right? And recall that also we could find COP as 1 over 1 minus Q dot L over Q dot H. And once I've got COP, now Q dot L becomes the only unknown on this side of the equation. Or I can solve this first law for the whole heat pump for Q dot L. Either way works just fine. But notice now I've got as many equations as I have unknowns. Find Q dot H. Q dot H gives me COP. COP gives me, or the first law with Q dot H gives me QL. If this is a test problem at this point, you'd be at 15 out of 25 points, probably 5 points for, basically you got 3 equations here, right? You got an equation down here, 5 points for this guy, and you've got either 1 equation, 2 equations, or 2 equations here, but in any other case, you would need 2 of these 3 equations plus this one, right? So you need 3 of the 4 equations I've got here to get to a solution. Now all you would need to do is go find properties. Remember when I said when we started chapter 3, I said, have that checklist handy the first 100 or so times you find properties in the property table. And then the next 1,000 or so times, you probably can do it from memory. I wasn't kidding. Now I've done it enough times, at least the next 100 or so times, you probably can do it from memory. Given P1, T1, you can figure out the phase and then go find H1. It's probably superheated vapor. Given the fact that you have the same pressure and saturated liquid at the exit, you should be able to find H2, which is going to be HF at that given pressure. And so if you do this, this tells me, hey, you know how to find your properties. Now it's just an issue of actually going and looking them up. Showing me, how to find the properties correctly is going to get you out of the 5 points that this whole thing is going to be worth. Get you another 2 or so. At least you're correctly identifying, hey, here's how I'm going to go about finding these properties. So that plus the equations, you're at 17 points or so. That's a C, or at least 17 and a half out of 25 is a C. That's how I would set up grading. Actually going and getting these properties, you're going to be at 20 out of 25. Going and getting a solution, that gets you to 25. That gets you A. Okay. All right, let's go look at solutions. I've got those in the notes here. At this point, I'm going to assume you know how to do everything else, like getting to an answer. If you don't, you really are behind at this point. You really need to start getting caught up. But you can kind of see that's how the rest of this is going to work. So here we go. Yeah, there's properties. H1, 271.22 kilojoules per kilogram. H2 is about 95.47 kilojoules per kilogram. Those plus the mass flow rate gets you, which is what we have here, solving this for Q dot H. That gets you an actual value, a number of kilowatts for Q dot H. And then given that and the COP equation, you can find the COP is 2.64. COP for a heat pump will always be greater than 1. COP for a refrigerator is probably greater than 1. And then once you've got Q dot H and the power input, you can use the first law for the entire heat pump, as we mentioned back up here. That's what they're doing here. They're using this expression, the first law for the heat pump, to find Q dot L. That is the remaining, or the difference between the 1.2 kilowatts going in for the power, 3.64 that's actually going out as the heat into the house. The difference between the two, the balance, is about 2 kilowatts, 1.96. Okay. I'm going to stop this video here. We'll just do an example on this one, and we'll pick up on the next one talking about reversibility and perpetual motion machines.